All right. So it is my great pleasure to introduce Doug Nychka as our STAMPS webinar speaker today. So Doug is one of the leading experts in spatial and spatial-temporal statistics, and especially the application of those techniques in climate and environmental sciences. He's currently a professor at the Department of Applied Mathematics and Statistics at the Colorado School of Mines. And he also holds a position, an emeritus position at NCAR, at the National Center for Atmospheric Research. And in fact, before he joined the Colorado School of Mines, he was the director of the statistics branch at NCAR, and he spent many years at NCAR working with the climate scientists in there. And I believe he's still collaborating extensively with NCAR. Sort of a special focus for his recent research has been computational techniques for very large spatial datasets. And I believe the subject of the talk today is related to exactly that topic. So with that, Doug, please take it away.
All right, thank you. Thank you very much. Very flattering introduction. As you were talking, I was just cruising through the gallery here, and man, what an amazing audience. I mean, it's like, you know, 3 colloquium audiences combined. So anyway, really nice to reach all of you today. Let me go ahead and start sharing my screen, and let's get going here. So this is a little bit of a visual introduction here. Let me clean this up a bit. All right. So what I'm running in the background here is an animation of the NCAR climate model, and it's important for you to realize several things about this. First of all, this is a huge code base, you know, on the order of millions of lines of code. It's focusing on showing you the clouds here, although a climate model simulates the entire Earth system. So that includes the ocean, land processes, atmospheric processes, and also sea ice. It's stepped on a very small time scale, and typically this is run over 100 years. The interesting thing about a climate model is that it doesn't actually compute climate. What we're seeing here is a simulation of weather, and the way we would interrogate the climate that this model embodies is we would treat that weather sort of the way we treat regular weather observations. We want to know what the climate is. We would take a 30-year average of them and apply statistics to it. So at some fundamental level, looking at these climate models is going to have to involve some data science, and that's really what my part of what my application is about. Okay, so let me kill this, and I'm going to bring up my talk. Let's see here. Let me share full screen. All right. So, Mikhail, is this visible to you? Are we all set here?
Yeah, they're all set.
Okay, great. So, deep learning, very sexy sort of topic, right now. Like everybody else, I've jumped on the bandwagon and I'm trying to use this. I have an interesting twist on this note, and that'll come out pretty clearly in the talk. Just a second. Okay. All right. You know, let me use this title slide to acknowledge the co-authors here. So primarily Florian Gerber, who is now at University of Zurich, did a lot of the basic calculations here. Maggie Bailey is a grad student at Mines, and she did a project that I'm just going to cite at the end of this talk. And Steve Sain is currently working at Jupiter, and he provided sort of the impetus and the motivation for Maggie's project. So we'll be seeing that at the end of the talk. All right. So I want to set the stage by just talking a little bit about very classical numerics, how we find a Gaussian cumulative distribution function, how we actually compute it numerically. Tell you about my climate application, a little bit about deep nets and how I train them. And we're going to evaluate these relative to maximum likelihood estimates. Return to that climate application. And then at the very end, this is probably only going to be about 2 or 3 minutes. I'm going to talk about Maggie's application and a totally different way of using deep nets to yet again do a statistical calculation. All righty. So here's what physicists call the error function. We think of this as the standard normal CDF, and then we also have the tail of the CDF, which is called ERF-C, I guess, error function complement. Well, how do we compute this? Well, if you're like me, I simply just fire up R, type in P norm 0.25, and there's the integral from minus infinity to 0.25 of that normal CDF. All right. So how is this really computed? Obviously, for those of you that have taught probability and statistics, one of the first speeches you give to your students is that this this integral doesn't have a closed form, has to be found numerically. Here's one route to that, and this is very close to what's actually programmed in R in C. So we have this ratio of polynomials in this reference by Cody. This is a ratio of a 5th degree polynomial to a 4th degree, and of course those coefficients are very, very carefully chosen to give highly accurate approximations, in this case to at least 14 digits. So there they are. We can look at these, and there's probably some reasoning behind these, but at the outset, why a ratio of polynomials? Why these leading terms in front? Why just this particular expansion for the tail for large values? It's all sort of mysterious, but nevertheless, it's in R. It's extremely accurate. It works. All right, so that's very, very classical situation. Let me give you the kind of thing I'm thinking about. So I like working with spatial data. Here's an example of a 16 by 16 spatial field. We can think about fitting a stationary Gaussian covariance function to this, and I'm thinking about 2 parameters: the range and a ratio of the nugget to the marginal variances. So I'm calling those theta and lambda. Very straightforward, classical kind of computation to find these MLEs. Step back a moment. This is really a function. We're taking this entire spatial field, 256 points, and we're mapping it into 2 parameter estimates, our theta hat and our lambda. Very particular mapping because we're finding the MLEs of this, but you can just think of this in general. This is just a complicated function, no closed form, but we can easily compute it in R using optimization to sort of whatever accuracy we want. Okay, Well, the connection here with deep learning. Here's a second. I'm going to have to put my cat away. Sorry, this is the first time that a talk has been interrupted by Carmen. The basic idea here is that deep learning networks are excellent at approximating certain kinds of functions. So really what this talk is about is maybe we can use deep learning networks to approximate the maximum likelihood function, the mapping from data to the parameter estimates. I'm also going to talk about another application where we're going to be estimating values of the parameters of the extreme value distribution in a similar way. Similar to the Gaussian CDF, the approximation works. It seems to work pretty well, but like that one that's ratios of polynomials, it's sort of mysterious what's going on. I'm going to probably mention this remark a few times, but let me emphasize that the difference between what I'm doing and what I understand traditional deep learning applications is that I am training this and testing it on quite an exhaustive set of parameter values and data sets. Florian is able to train these networks on 1 million test cases. And so in doing that, we really do feel comfortable that this approximation works. It's a very exhaustive kind of sieve that we've run this through. That's a little bit different than having a limited training and testing sample in some of the more image analysis related cases for using deep learning. Okay, let me sketch out what the climate example is. There's a little bit of details in here that I'm going to gloss over. But the overview of this is we've run the NCAR climate model 30 different times. We've gotten out these fields, which you can think of these sort of like temperature fields, although they're not exactly that. We have 30 because we've run an ensemble of 30 different runs of this model. And what I'm showing you here is the first 8 fields for just over North and South America. We see variation among these, and really the spatial problem is to try to quantify what that variation is. It's non-stationary. Obviously, there's a little bit more variability over land, and the coherence is a little bit less. The spatial correlation is a little bit less over land than compared to ocean. And there's other sort of distinctive features in this. So a complicated non-stationary process. What the goal is here is we would like to extend this sample beyond the 30 member ensemble and actually emulate these fields using a statistical model so we can simulate many more. The idea is that the variation in these fields is used to try to understand climate change and the uncertainty in future projections of climate change. In order to quantify the uncertainty, we want to go beyond just this 30 sample, simulate perhaps thousands of these cases cheaply, and that'll allow us to understand more what the tail probabilities might be in these results. So that's the overall view, and I can field more questions about that if people want to know more about the application. However, let me focus on the part where we're going to use this deep learning approximation. That North and South America image I showed you has about 13,000 grid boxes. What we want to do is fit a local stationary spatial model to this. And the way we're going to do this is very simple. And it sort of feels a little bit like a kernel approach here. We're going to have a moving window that's going to be 16 by 16 pixels. Wherever that's centered, we're going to estimate a small number of covariance parameters for our spatial field. And we're going to do this at every possible position for this window. So we're going to end up with on the order of 13,000 spatial parameter estimates. And then these are going to be used for subsequent things. I've highlighted this blue step because that's what I'm talking about today. But keep in mind this is embedded within this larger goal. And Ashton Wien's a recent University of Colorado PhD that I co-advised. This was sort of a centerpiece of his dissertation. Okay. In estimating these covariance functions, what we're going to do is do a very simple switch. Instead of doing a maximum likelihood optimization, we're going to pull out our convolutional neural net or our dense neural net and use that to estimate the covariance parameters instead of the MLE. And we do that with the confidence that these are as good as the estimates of the MLE by and large. So in some sense, we're not doing anything new. And it begs the question, so if you have the MLEs for these things, why are you training a net to give you similar answers? And the answer is well, the neural nets run quite a bit faster. In fact, for this particular problem, let me just step back here. This particular problem, running the 16 by 16 windows over these spatial fields speeds up by a factor of 100. So we're, to put that in context, we're going from a few hours to a few minutes in terms of speed up. Let's see. And John, did you?
Yeah, I just had a naive question. So when you do the convolutional neural network, there's translation and variance. I was wondering if whether or not the kernel is centered on an ocean or land is taken into account somehow.
So the translational invariance that's being exploited is the fact that we have this mapping between data and the statistical parameters. Now, every different window can give us different estimates of those statistical parameters, and we'll actually see that the covariance estimates over the ocean are very different than over the land. So, by analogy, it's sort of like the convolutional neural net is like the function x squared, and we can give x squared different inputs and get different outputs from it, although the x squared stays the same whatever inputs we're given. Does that help, John?
Yep.
Okay, great. All right. Just a brief review of spatial statistics. So I'm focusing on the stationary Matern family. And in fact, we're looking at a smoothness that is, let's see, is one in this case. What I wanted to do, though, is also consider the special case when the smoothness parameter is 0.5, because that's sort of a nice simple form, and it's easier to visualize what the heck this is doing. So remember that a covariance formula is a recipe to tell us how points in a spatial field are dependent. And For it to be stationary and isotropic, we have this function is just related to the distance between 2 points. The way this works is we look at the distance between 2 locations, x1 and x2, scale it by that range parameter theta, take the negative exponential of it, multiply it by sigma squared, and that is the covariance between these 2 locations. And so the parameters that we're interested in in a spatial analysis would be, for example, the sigma squared and theta. All right. And as I said, I'm fixing the smoothness. It's still sort of a bit of an open question whether we can actually estimate that from data. And I'm not really sure about that in this case. Let's see here. I wanted to take this another step further, and I apologize. This is a little bit of going into the weeds here in terms of spatial statistics, but there's an important punchline to this, and I'll give it at the end of the slide. So what we're seeing here is that this is a particular value in one of those spatial fields from the climate model. And we're decomposing it into that smooth function that's following that Matern process that I just walked you through. And another part, which we're just going to call white noise. Traditionally, this is called measurement error, although that's a bit of a red herring. Really, what that E sub x is doing is it's all the fine scale spatial variation that we can't explain in G. Or another way of saying that is that G is the spatial predictable component for these data that we observe. The stuff that we can't predict, we're basically modeling by this white noise process. The white noise process has a variance tau squared. And so what we have here is 2 separate sources of variability. And really, part of the key of a spatial analysis is to understand what are the relative sizes of these. And this is classical in engineering. Really, what we're trying to understand is what is the signal to noise ratio here. The way I'm parameterizing that is the noise to signal ratio. And my thesis advisor was Grace Waba, and this parameter lambda comes from thinking about smoothing splines. So basically, I am caught in this time warp of parameterizing things this way. But anyway, the shortcut here is it turns out that if we estimate this parameter lambda, the noise variance to signal variance ratio, we can get the MLEs for sigma squared and tau squared very easily as a closed form. The theta, we just have to find the MLE. This is the correlation range. There's nothing we can do about that. Okay, so what's the punchline here? I'm going to tell you in a moment the training design that we use to fit our neural nets. That design basically devolves into choosing a grid of parameters to simulate spatial fields and use that to train the neural net. How do we choose this grid of parameters? It's going to be a 2-dimensional grid. It's going to be in theta and lambda, and how that's chosen turns out to be important in this problem. Originally, Florian just chose lambda to be equally spaced on a log scale. I had a slightly different version of that, and it turned out that this other version, this other transformation of lambda tended to work out better. So there's a subtlety in doing this that you have to think about. No surprises there. This is just good old design experiments. I mean, you want to think about how you vary your your inputs when you're trying to study a response surface. Okay, I'm going to gloss over what the likelihood is. As I said, this is very classical stuff. I'm not proposing any sort of magic to getting around finding the maximum likelihood estimate explicitly. So here's the likelihood, and what I highlighted in red, if you want to go back over these slides, is that concentration from going from 3 parameters just to this noise to signal ratio lambda. For those of you that are don't work in spatial processes, here's just an example of what these critters look like. What I've done here is I've created fields that have a large white noise component all the way down to fields that don't have a white noise component and are just the smooth component G. Across the rows here, I also have increasing correlation ranges. And so it's particularly apparent here where no white noise component, shorter term correlations, all the way down to much longer term correlations. Let's see here. One thing to note about this is that I'm being pretty aggressive. I'm actually proposing correlation ranges that extend beyond the spatial domain. So these are fairly long correlation ranges. And of course, that's what we want to do when we're taking these small 16 by 16 windows. We want to have a little bit of power to try to estimate longer term correlation ranges, because we know a priori that that's going to happen at least over the ocean. Okay, so there's our different possibilities. As I mentioned before the talk, there's an alternative way of thinking about spatial data, and that's with the variogram. And I'm not going to write down an explicit formula for the variogram. I'm just going to tell you a little bit in words what it is. We have our spatial data set. Every value has a spatial location. We're going to look at all possible pairs of our data. So we're going to have a difference in the spatial value. We're going to take that difference and square it. And then we're going to connect that to the separation of those 2 points. So we have a lot of different pairs, a lot of different pairwise distances. And this is what how we assemble a variogram. So along the axis here would be the distance of separation. This green cloud of points are all these different squared differences of the spatial fields divided by 2. And what we see here, this black line, is the mean curve over these. So we see a little bit of signal in these, but tremendous variability as we sort of, especially when we have a lot of white noise in here. So the intuition I have is that this variogram, while it's pretty quirky, while it's tremendously noisy, it can act as an approximate sufficient statistic for the covariance parameters. That if we look at this black line, this black line is in some sense equivalent to the correlation function or the covariance function as just a function of distance of separation. We see that there is some sort of signal lurking in this, that when we get down to here, longer correlation ranges, no white noise component. Certainly this looks quite a bit different than this one. Maybe the neural nets can find these true covariance parameters just by giving it the variogram. And, you know, I would say in terms of this talk, to me, that was the biggest surprise. And in fact, it seems to work. And it's still a little bit confusing as to why this works. Alrighty, here is my parameter space, these great gray lines. As I've been mentioning, we have a correlation range, that's our theta. We're looking at the log of this noise to signal ratio, but we're actually sampling these in a slightly different way than just equally spaced on a log scale. And I'm not going to take the time to go into that in too much detail, but just to say that if you're familiar with what a smoother does in terms of effective degrees of freedom, I'm basically pegging lambda to give us equally spaced effective degrees of freedom. So we have 256 observations here. Basically, lambda is chosen so that we get equally spaced effective degrees of freedom for our spatial estimate from 1 all the way up to 256. That tends to work better than just other choices. As I mentioned, it's easy to simulate these fields. We're actually simulating 1 million fields. Those 1 million fields comprise about 40,000 unique parameter values. So I hope that you're getting this sense. I mean, this is what Florian and I think. We're really killing this problem. I mean, we're exhaustively sampling sort of what Matern fields look like over these parameter choices. And so that gives us confidence that if the nets actually do well, we've really found a reasonable approximation here and can trust it. Okay, let's see here. I'm not going to spend too much time telling you what a deep net is, and that's partly because there's lots of excellent tutorials and explanations out there. And also, to be honest, I'm sort of using this as a black box because I feel confident that I have an excellent training sample, and I'm testing also in a very rigorous kind of way. I wanted to though direct you to this wonderful textbook by Michael Nielsen. When I was teaching, I used this for my class. He comes from a physics background and just a really great explanation of what neural networks are and deep learning. So it's free to download, very easy read. You'll also be amused. There's certain places where he really struggles to explain simple statistical concepts, and that's also fun to see. Sort of a very smart physicist also has some blind spots or difficulty in pedagogy and topics that we just take for granted. Anyway, okay. So what is a neural network? I'm going to focus on this middle slide here. The 3 values are sort of like our observations. These 3 values get fed into these 4 neurons. And what a neuron does is it's basically a machine, a function evaluation, where it takes its inputs, weights them, takes that linear combination, just sums up weights times the inputs, and then applies a nonlinear transformation to it. That nonlinear transformation is fixed. It's typically a sigmoidal shape or just 0 when the value is less than 0, and then the value itself when it's greater than 0. That's called the rectilinear transformation. So each of these neurons operate on their inputs and they produce an output. This number is then fed into other neurons down the train here. So I've just shown 2 hidden layers here, but actually a deep net has many hidden layers where outputs from one set of neurons are fed in as inputs to the next layer. And then finally, at the very end, I mean, you have to get an answer out of this. At the very end, we have, say, if we want a single value, we have a single neuron, which takes all the outputs from these intermediate neurons, this hidden layer, and then produces a single number. Okay, so the key here is that the nonlinear transformation is fixed. However, all these weights that are applied to get our linear combination for all these neurons is being estimated. So we have lots of parameters. Let me show you a slightly different take, which is the convolutional version. The convolutional neural net is also a linear combination of data. But since you're expecting your basic problem to have this image format, you're organizing everything in terms of taking linear combinations over images. So to get started here's a cartoon of what we might like to do. We're taking a linear combination of these 9 pixels in a 3x3 block, and that feeds forward to give us a single value in the image in the next layer. And then we jog this over 1 pixel, and we do that weighted linear combination again, and that gives us the next pixel over. So this 2x2 image here is what we're seeing in the next layer. And then you can actually imagine taking weighted linear combinations of those and then applying the nonlinear transformation to get even a subsequent layer beyond that. Now the elaboration of this is that rather than just thinking about one linear combination that we're applying to all the different 3x3 combinations here, we actually have several of these going in parallel. So we'll create one image based on a set of filter weights, another image based on another set of filter weights. And these weights, of course, are being estimated from the data. This is the bulk of the training. Okay, let's get to what I did here. Here's an example of the convolutional neural net that Florian and I devised to estimate the parameters theta and lambda based on these 16x16 images. And so you can see that there's actually quite a bit of intermediate stuff going on here. At the first step, I'm looking at 7x7 filtered images and taking linear combinations of them. How many different ways am I doing this? Well, I'm doing this 128 times. This gives us a new set of images, actually 128 of those, and I'm going back and filtering those also. And then finally, at the very end, I end up with, once I do all of these convolutional neural nets, I end up with 500 outputs. And then these are fed into just a single dense set of neural networks, which eventually produces our 2 outputs. So very complicated architecture. We found this sort of essentially by trial and error. And more than 600,000 parameters. So, as a statistician, there's always this sticker shock of, we're trained to be parsimonious and, we don't want too many parameters relative to data. Even with a training sample of 1,600,000 parameters sounds like too many. Turns out that in the training of these, there's a lot of regularization and it's almost like variable selection built in. And so you can actually effectively train networks like this to work pretty well. Okay, so here's my results slide. And what we're showing here is the difference between our nets applied to a test sample, which of course is completely independent from our training sample. It's applied to a test sample over different values of the lambda parameter and different values of the range parameter. And I'm just showing you how well this is doing just based on box plots of these things. I've subtracted off the true parameter. So we want all these box plots to be around 0. And in fact, they are. The variability here is really just showing us the sampling variability of our estimates relative to the true value. So what jumps out at you, I guess, first of all, is these are all around 0. We see a little bit of bias when we use variograms to estimate the true parameters. The other interesting thing about this is here are our MLEs. Now we can find the MLEs because we're only looking at 10,000 test samples. What we do not do is train the net on MLEs because that would involve finding MLEs of 1 million test cases. And at that point, that sort of begs the question of, so why are you interested in finding these so quickly if you can actually just pump out 1 million MLEs to train this thing? So we're actually training on the true parameters. I'm relying on some standard statistical theory that says that the maximum likelihood estimates for larger sample sizes and unbiased estimates is in some sense the best you can do. It has the smallest variance. So if I'm coming up with a net solution where the variances seem comparable to what the MLEs are, I'm going to declare success and say that I am close to the optimal solutions here. So notice that this is very different than the typical deep net learning talk where we're saying we have images, dogs and cats, and we're trying to train these to see the difference between dogs and cats. I know exactly what I want. I have my benchmark, and I know sort of this is in some sense the best we can do. What's interesting about the nets is that in some cases they have a little bit smaller variation, like over in this part, than the actual MLEs. And I think what's happening there is that we're getting sort of a balance of mean squared error where the MLEs may have less bias and larger variance. And here we have maybe a little bit more bias in our estimates and smaller variance. So estimates of lambda doing pretty well. Estimates of the range parameter doing pretty well. And notice that both the convolutional version and using this variogram as a sample, as a approximate sufficient statistic is also doing surprisingly well. Okay, so back to the to the climate example. So remember, I have 12,000, roughly 13,000 grid boxes here. I'm running a 16 by 16 window across these data, estimating the this lambda parameter and the range parameter. And I'm just reporting those results here. So here's our MLEs, and this is a small enough problem where we can actually find the MLEs for all of these windows. Florian felt that the neural net version worked a little bit better for this case, so that's why we're reporting that. And you know, there are differences between these. It's not a perfect approximation. We can argue those differences away in two different lines. One is to say the visual impression here is very similar. And if we were actually trying to come up with a global statistical model that's describing the non-stationarity of this, and then re-estimating that, we'd probably be led into coming up with similar statistical models based on looking at this picture versus this one. The other way to argue this is to say, hey, these are MLEs. They're not the true parameter. We know that our neural nets are estimating the true parameter with comparable variance. There's no guarantee in the way we've done this that the MLE and the neural net are actually perfectly correlated with each other. It's just that they have similar accuracy. So we could also argue maybe the differences here are simply just due to sampling error, and we have two good estimators and they're slightly different. So there you have it. The timing here, I probably, as you can imagine, I wouldn't be giving this talk if the timing wasn't dramatic. When we apply the convolutional neural network to these data, it takes on the order of tens of seconds. Doing the MLE takes on the order of hours. I want to make a very simple point, and I feel like maybe I'm preaching to the choir here, but if you have a tool in R that speeds up a calculation by a factor of 100, all of a sudden, you're starting to think about doing things in an interactive and exploratory way that you wouldn't have thought about doing before. And this is an example of that. If we had this software available in R, and we're actually very, very close to building that, it would mean we could read in large spatial fields like this, find local maximum likelihood estimates, take a look at them, and then just sort of decide on different kinds of models or different kinds of transformations of the data. I had a colleague when I was at NCAR, Rich Loft, who said, if it takes too long for me to get the answer to my question, I usually forget what my question was. And I would argue 1.5 hours to try to do something that is fluid and flexible in terms of exploratory data analysis just doesn't work well, at least for me, and maybe for most people. Okay, so that's the argument for the timing.
Doug, do you have about like 8 minutes or so left?
Okay, sounds good. I'm just about to wrap up here. Let's see. Several things very quickly. The natural question that I'm sure you're interested in is, so this is all done for regular grids, and in fact, there's probably other ways to get fast approximations to the MLEs using regular grids. There's sort of spectral transformations, and you can work off the periodogram that also might give you fast estimates. Really, the interest here is to focus on this variogram version and see if we can also get that to work for irregularly spaced data. The variogram is well defined for irregularly spaced data, and we've at least seen that the nets work well in that case for the regularly spaced data. These are some preliminary results that Florian has worked on, and really all I'm just showing you is our true values based on a test sample, and then our predicted values by the net. And so this is lambda, and this is the range parameter. And so what we're seeing here is some skill in this. It's still an open question as to whether or not we're still going to capture the same kind of variance or mean squared error is what we're seeing with the maximum likelihood estimates. But that's a sort of an ongoing project. All right. Some loose ends here. For different sample sizes, the variogram has different amounts of uncertainty. How do we adjust those in the neural net? The other issue is that there's more complicated covariance models where the parameters are difficult to estimate, and we can entertain trying to train neural nets to do those. And really the key here is that many of these models, even though they have complicated likelihoods, are fast to simulate. So we can simulate zillions of training samples with the hope that training the net will then be able to fall into what the true parameters are. And then finally, besides just estimating the parameters, we'd also like to get on uncertainty quantification of them. And that may involve sort of including features of the likelihood surface besides just the estimates. All right. So my guess is I have about a minute here, and I'm just going to talk through the application because it's fascinating. And I'm not going to show you the results. It's going to be pretty clear what we're going to do. So Steve Sain works at Jupiter. They do a lot of risk analysis related to flooding for often urban areas. I'm showing you a map of Hawaii here and a blow up of part of that. And you can see that there's a residential area here. Jupiter runs very extensive simulations under different weather scenarios. And for each of the pixels in their simulations, and we're talking about millions of pixels across, say, like this island of Oahu, they collect data, and they're interested in estimating the extremes that occur here. So the statistical problem is that we have many samples of data where we would like to estimate the tail of the distribution. And we would like to do that quickly for the same reasons of exploratory data analysis, modeling, non-stationarity, and everything. So our approach here is to take the data, create a very finely binned histogram, and then use that to train a neural net to find the parameters when we're fitting a generalized Pareto distribution. And that's a standard distribution to estimate extremes in the tails. And what we're finding is that surprisingly seems to work okay. And so it's still research in progress as to whether or not we can do as well as maximum likelihood, but so far that seems to be very, very promising. All right, so let me, I've posted this talk so you can take a look at that. Let me just wrap up here. So we're going to exploit fast simulation of statistical samples to train a neural net. Neural nets can accurately reproduce statistical computations, big deal, but they evaluate often much more quickly. And I should mention that's partly because of the magic of these TensorFlow libraries that underlie the neural net computations. Training and test samples provide a rigorous way to ensure that the neural nets actually give good approximations. And again, that's a little bit of a difference than the typical machine learning application where your training sets are limited. All right. Thank you very much.
Thank you very much, Doug, for the excellent talk. So let's see if you have any questions at this point. So if anybody has a question, you can either use the raise hand button or you can put it on the chat box. If anybody has a question, now is a good time to ask that. Okay, I see
Okay, I have a
one from
question.
Michael. Okay, I think Michael's time was first, so let's go look at Michael's question first, and then we'll go with Galen. So Michael is asking, how are you dealing with curvature of Earth?
How am I dealing with curvature of the Earth?
Yes.
Yeah, so we're dealing with that in a simple way. What we're assuming is locally stationary, local Euclidean in longitude, latitude, and we're going to let the variation in the range parameters take care of that. Now, there's still going to be an issue in so that might make sense in terms of the longitude. In terms of the latitude, it's a worse approximation, but really we're looking at pretty small patches here. So a varying range parameter, we're assuming it is going to take care of the curvature.
Cool, thank you. So I think Galen had a question. So Galen, would you like to ask your question?
Sure. So on the plots where you were showing the results for how accurate the neural nets were, I noticed that there were kind of two sides to each of the plots. There was like a side that was colored red and a side that was colored blue. And I was just wondering if there was any meaning behind that.
Let me let me find that here. Okay. I'm embarrassed that this is the first time I've noticed that. So Florian drew these plots, and we actually talked quite a bit about them. And I never thought to ask him what that was. It may be that he's making well, yeah, it's a mystery to me. Sorry. Clearly there's not too much content to it because I don't know what it is. Yeah. I wish Florian was here. I think it may just be an artifact of using lattice graphics or ggplot to draw these. Yeah. Good question.
So we have at least one more question in the chat box that just came in from Eric Feigelstone. So let's see. So Eric is asking, classical kriging also uses variograms to estimate theta and lambda in modeling of non-stationary spatial processes. Can your approach be considered as deep learning extension of kriging?
So that first point is what I didn't tell you about is, yes, you can estimate parameters theta and lambda directly from the variograms. They are not very good. I mean, there are these fancy ways of using nonlinear least squares. They don't work very well. I was certainly open to be proved wrong, but this is sort of the common folklore. Can your approach be considered as a deep learning extension of kriging? I would say no. And that's and I'm going to take that position to be very conservative here and to say, I'm just trying to do spatial statistics, and I just want to do these things fast. And it's a little bit like, I just want to find the normal distribution function, and I don't care how it's computed as long as the approximation is accurate and it comes fast to me. So I'll just answer it that way.
Yeah, and I believe there are like all these recent papers on like deep Gaussian processes and things like that. That's probably more like a deep learning extension of kriging, I would imagine.
Yeah. Yeah, so I see, may I field Dorrit's question?
Yeah, I was just about point, I would like to actually expand that a little bit because I had a related question. So Dorrit is asking about the, that your training sample covers the range of parameters. So I had sort of a similar question. I also want to add on that, there's also a distribution on that range. So how, and you briefly mentioned that these results are sensitive to the way you choose the distribution, potentially the range. So could you explain a little bit what kind of dependence on that distribution and the range did you find when you did these experiments?
Yeah. So, that's an excellent one. So I would say in practice, what we want to do is we want to train the neural net so that when we do the testing, we understand when the neural net is going outside its range of accuracy. And at that point, we would just say, sorry, this isn't a situation where it's really trustworthy. And if you were watching, our parameter space that we're training is actually much larger than our testing space. And so, I would stick to that testing space as where we're only going to use the net. It's a little bit tricky because we have to use the net's estimate as the way to corral these things into the accurate region. But this training seems to work so well. I think we can probably deal with that.
Cool,
Yeah.
thank you. I believe we have a question from Anne. So Anne, would you like to go ahead?
Yeah.
First, thanks for a great talk. Really enjoyed it.
Yeah.
I have a follow-up question on the sampling and the parameter space. You mentioned that the simulations are really fast. Do you mean like if you choose a parameter set, you can simulate the whole spatial temporal image quickly?
Yes. And it's for two reasons. First of all, we're only looking at small numbers of observations because we're anticipating this is just a moving window. So we're actually not thinking about looking at very massive spatial data sets. So the simulation is essentially a Cholesky decomposition and a multiplication of a matrix about 256 by 256. So very, very fast that way. The other thing is that we're looking at many realizations of the field for a given set of parameters. So we're actually saving all our Cholesky decompositions and reusing them. So
what do you mean with different realizations?
We're looking at 40,000 different parameter combinations,
right.
But we're actually simulating more than 1 million cases. So obviously there has to be some replication there. Let's see. So the analogy is drawing a sample just from a normal distribution, and it's some number, and I can draw it again, and it's going to be another number.
Yeah,
but
I think my question is: are they independent? Like if you
yes,
draw for
yes.
they are IID. So if you take the same parameter point, you can draw 1,000, but
yes,
the independent,
yes,
the
yes.
whole spatial field.
Yeah, that's right.
Okay. Huh,
Yeah.
So you have 40,000 in this example you had covariance parameters, but you could draw more, right? So it's not really a computational issue to generate more data. Because 40,000 is kind of small.
Except generating the train, every time you change the parameter values requires a different Cholesky decomposition. So, depending on how many Cholesky decompositions you want to do is really the limiting factor.